Now coming to intramolecular Friedel graph. Okay. Now let me give you this example. See, when this is taken with the Lewis acid, what is the product formed? Let's see. Initially, this chlorine, of course, goes out along with the bonded pair. I mean, it actually donates a pair of electron to aluminium, the Lewis acid, aluminium chloride. Okay, as a result, no doubt AlCl4 minus goes off. So here we get a positive charge, right? Now, to this positive charge, I can simply show it this way. Or else we can even take this way, minus here, plus here, if you want more clarity. That's I think better. Now this minus attacks, right? So now this one. We have 1, 2, 3, then 4. 1, 2, 3. Then of course the fourth one. Fourth one got connected. We still have this positive charge, and the same fourth carbon, of course, has, I mean, the carbon that got connected has got a methyl group, this one, right? Now, let us take a hydrogen out and do this so that the positive charge goes up. And this H plus can of course be removed along with the AlCl4 minus that is being removed in the first step. So let us consider this as Cl, AlCl3, right? Minus here. Now this Cl minus in fact abstracts a proton, H plus. So that is how we get this, then this, and this one. And the byproducts that we get here are HCl, along with that the Lewis acid, AlCl. So, okay, so this is a very good example for intramolecular Friedel graphs. reaction. Now, one more example. Here, let us consider this. With HF at 0 degrees centigrade, product formed is. Now, okay. See, in the presence of HF, I mean an acid, bond goes towards this carbon, and then in this case also it can be written as H plus and F minus. Of course, the H plus is given. Okay. Now, anyway, we got a 3-degree carbocation. Look at this. One. This one, right? Now we got a positive charge at this carbon. Only 3 carbons. Now let us do this way. As this will actually give us okay, we'll get a positive charge here. 1, 2, then 3. That's it. We have only 3 carbons here, right? And see the third carbon that actually got connected to the basic benzene ring, the original one, has actually got 2 methyl groups, right? I think it's okay. Now let us do the same thing again. Let us take a hydrogen out. Let us take this bond to the rescue of the positive towards the positive. That's it. We get this final product. Here you can use a fluoride to abstract H plus. That's not a big deal. So minus H plus. This, this, this. Okay, right. So this is how the intramolecular Friedel reactions take place. Right? Now let us go for the orientation. In electrophilic substitution reaction. Let me give you clarity on what orientation is. See, we may have 2 different types of groups. Let this be the electron withdrawing group, and say this one just the ring with no group connected to it. No withdrawing, no releasing. Come on. Let us consider a releasing group on this. Okay. Let this X be the releasing group. Now, when I say electron withdrawing group, it is this. And when I say releasing group, it is this. You know, electron withdrawing groups generally deactivate the ring. That is, they decrease electron density in the ring. Right. So these electron withdrawing groups are also known as deactivating groups. See, in electrophilic substitution reaction, electrophiles approach the ring readily only if the ring has electron density, too much of electron density. So in this case, when the electron density in the ring is getting decreased because of the electron withdrawing group, generally the electrophiles do not approach. So when we see the order of reactivity, it will be this. It will be less when compared to the basic benzene ring. And let me also tell you that the deactivating groups are all meta directors. But for this, I need some more time to explain. All electron withdrawing groups are all deactivating groups are meta directors. I'll tell you why and how later, within no time. Now, when you go for electron releasing group, you know, it is very clear that the electron releasing group is activating the ring. Generally, the electron releasing groups activate the ring. I mean, increase electron density. We have already seen this in the ring. See, when there is more electron density in the ring, obviously, the electrophile readily approaches. Now, this of course can be taken as the order of reactivity. Of these three, in general, we'll have only these three varieties. With no group at all on benzene ring, with a withdrawing group attached, or with a releasing group attached. Generally, the releasing groups activate the ring. So, electron density increases in the ring. As a result, electrophiles approach such a substrate readily. Now, let me also tell you that these are ortho-para directors. See, electron releasing groups are ortho-para in nature. Electron releasing groups, or you can also say activating groups. Okay. So this is the basic information about the orientation in electrophilic substitution reaction. Let us now see why are these substrates with electron withdrawing groups act as meta-directors, and why those with electron releasing groups act as ortho-para-directors. Now, what are ortho-para-directors? In general, the activating groups are ortho-para-directors. Let us take an example. Take phenol. In fact, OH group on benzene. You know, OH group is a plus M. Of course, minus I. But plus M anyway dominates. And look at this. It is a releasing group. It is, of course, activating. So this carbon. Now, we get a negative charge here because this carbon is gaining the electrons. Then this, of course, this oxygen is still having a pair of electron. So let me put a positive charge. Now, negative gets delocalized. Come on. This again. Towards the carbon. Now, finally, see the basic difference between the first and the last one. You got difference in the position of the pi bond. And see the thing that has actually happened here. You know, you got the negative charges. Nothing but the electron density centers at ortho and para positions, but not at meta. That means the activating group or say the releasing group is increasing electron density at ortho and para positions, not at meta, right? Activating groups release electrons and of course increase electron density at ortho and para positions. Whereas electron density at the meta position remains the same. So now tell me, where do the electrophile attack? Where do the electrophiles attack? Obviously, they go to the place where they have got more electron density. You got more electron density at ortho and para position. So obviously, it approaches the ortho and para position. So these activators are generally referred to as ortho para direct. Okay. Activating groups increase electron density at ortho and para positions, leaving the meta one. Therefore, electrophiles approach or say attack at ortho and para positions only. So these are called ortho para directors. This is what. Hope this is clear. Electron density is increasing only at ortho and para positions. That is very much clear from the negative charges that have been generated at two ortho positions, this and this, and a para position, I mean this. Okay. So all ortho para directors, I mean all activators are ortho para directors.